Okay. So good afternoon, everyone. This is GeoJackets from Georgia Tech. I'm Rashid Davis, and my other group members are Aryang Young and Jiansheng Zhang. We'll be presenting the work we have done for this project. And all right, so for our problem statement, as a problem states, we have a 3-meter radius circular tunnel, and is to be driven at a minimum depth of 60 meters in weak rock. A horizontal fault is located at a depth 56 meters, and there's a water table that is located at the ground surface, and the fault acts as a barrier to the water table, to the water. So the bottom of the water table is unsaturated. The horizontal stresses are 0.4 to 0.6 times the vertical stress. And from the PowerPoint slide, you can see a sketch of the tunnel model in figure 1. The model presents the rock at a depth of 40 meters to 80 meters and 20 meters around the tunnel, which is also the dimensions used in the numerical simulations that we did. The red layer in the figure represents the location of the fault, and the tunnel with a radius of 3 meters is at a depth of 60 meters in this figure. So the objective of the project is to find the minimum depth of the tunnel with a factor of safety larger than 1.5, and the probability of slip to be less than 5%. Oh yeah, so here. Okay. Okay, so some of the properties of the weak rock are and the fault are given in table 1. And based on the given properties, other properties can also be calculated. And we used or is given a coefficient of lateral stress to be 0.5, and the Poisson ratio was 0.33, which we used. And since this rock is relatively weak, we use a Young's modulus from a rock of similar properties in literature. And the factor of safety equation that we use to calculate for this project was of a stress over strength ratio. And we use a Gaussian distribution, and we use this to get the variance based on the coefficient of both. So these are some of the assumptions that we use for our problem. And the rock we assumed was elastic and homogeneous and isotropic. And the vertical and horizontal stresses are uniformly distributed throughout or along the tunnel. The vertical stresses are purely an overburden stress, and we also assume that the properties were statically independent. The analysis that we used was a Kirsch solution to determine the stress condition around the tunnel. And based on the Moore-Coulomb failure criterion and the tensile strength, the factor of safety, and the probability of slip of the fault, we were able to get all our solutions from a theoretical standpoint. And our numerical simulation that we did, we used a program of FLAG2D. Yes. Okay, so for our analysis methodology, here shows some of the details of how we did our theoretical analysis. With the overburden stress, we found the stress around the tunnel and the fault based on Kirsch solution. And the strain based on the elasticity. Right. Okay. And the failure criterion also are the Moore-Coulomb criterion and the tensile strength. To take the probability into account, we use a simple fact in the Gaussian distribution, the probability of the values are larger than the mean, or 2 times the variance in the Gaussian distribution. And we found that in the Gaussian distribution is 0.9 0.9545, which is about 95%. To meet this requirement for all the values provided with the coefficient, with this coefficient of variation, the values will be changed to the mean instead of, will be changed instead of the mean. Okay. Next slide. Okay, so for our numerical procedures, we use numerical simulation, and we provided a template and made minor changes to the code. As a code for the requirement, so we calculated the bulk modulus and the shear modulus based on the elasticity, and also we used the function of factor of safety to get the factor of safety result. So here's a code that we use and the template. Our numerical results with a tunnel depth equal to 16, with a tunnel depth at 60 meters depth, there are tensile stresses that are located around the fault, and it decreases the factor of safety significantly. And with the tunnel depth 2 or larger than 62 meters, the tensile strength diminishes drastically, and the results of the factor of safety are around like greater than 2 for this, or approximately 3 in both cases at 62 and 63 meters. For the numerical results, we also check the horizontal and the vertical stresses. The tensile stresses occur on lateral tunnel wall and the faults. It's important to note that with the tunnel depth equal to 60, there are horizontal tensile stresses, and this indicates that the fault may slip, and this depth is not the best choice. By checking other tunnel depth at 62 meters gives a more promising result and at a much safer factor of safety as well. So here are our theoretical analysis. We checked based on the Kirsch solution. The red line indicates that that there's a failure in shear stress based on the Moore-Coulomb criteria. We can see that that on the fault for the tunnel depth equal to 60 and 61 meters depth, the shear strength, the shear stress is over the red line. This actually indicates that a failure is happening on the fault. And for the tunnel depth of 62 meters and 63 meters, the green line is below the red line. So this is not over the failure stress. Okay, so for the factor of safety, we also calculated the factor of safety to find the values that are larger than 1.5. We can see that for the factor of safety with a tunnel depth of 62 meters is larger than 1.5 along the fault. And this is consistent with our numerical simulations that we found. So when comparing with the numerical model, we found that there was one issue was found, and we checked the stress around the tunnel with the theoretical analysis. The red line here in the figure is the failure stress based on the Moore-Coulomb criterion, since there should be no radial stress around the tunnel wall. If we check in the y direction, stress and the x direction as well, the values of the orange line when theta is 0 or 80 degrees are also located in the figure. And it means that the rock will fail at this depth given and at a high probability as well, since the rock is very weak. So this is also the key risk for that depth at 62 meters. Okay. Okay, so for the second fault, we can see that there are stresses at the different depths, and yeah, so this is also the analysis for second fault as well, and we did the same methodology as using curve solutions, and we found that in the second fault, the results are very similar to the one of the first fault, and is reasonable theoretically, because a curve solution should provide symmetrical solutions. Okay, so on the alternate scenario, we also modeled the second fault in FLAC 2D with a depth of 62 meters and 63 meters below the surface. And we found that 62 meter is still a feasible depth for the tunnel. And the figures show the stress fields and the distribution of stresses as well. So here are the key risks that we found from this project, and basically to reach an agreement with both the theoretical and the numerical aspects from the curve solutions to the FLAC 2D model, we found that the minimum tunnel depth should be 62 meters. However, the tunnel can collapse, as mentioned before, with a depth of 62 meters. But given the risk of building a tunnel around a weak zone, the supportive construction method would suggest that it will prevent this collapse during excavation and deformation of the plastic zone. Tunnel boring machines can, we suggest tunnel boring machines as a possible construction method to compensate for the key risk of this weak zone at 62 meters. And this is used to excavate models with drilling, and it will reduce the effect of stress concentrations in potentially unstable areas during the excavation. Also, grouting weak zones will also help provide a more stable excavation process, and it will minimize the risk of possible over excavation that may occur. So using the tunnel boring method, it is possible to expect a higher factor of safety, and this will increase the stability in the weak ground. In conclusion, we approach both theoretical and numerical model analysis to determine the stresses and deformation on both of the different methods. And we suggest different solutions depending on the number of faults under the construction area. If one fault exists at 56 meters, the minimum depth of the tunnel is 62 meters. In order to mitigate the risks of the tunnel construction and the rock failure in the weak zone, we would suggest tunnel boring method and grouting as well as possible solutions. And yes, so thank you. That is, and yeah, so that's the end of our presentation. We will take any questions. These are references, and sorry for the technical difficulties in the beginning.
Thank you, team GeoJackets. Judges.
Oops.
I think we can stay. Yeah, sorry, go for it. Sorry.
So I have a question. You chose a Young modulus and cohesion. Then when you did your analysis, you simply chose for the strength parameters values that were 2 standard deviations below the mean value. Do you think there could be a relationship between your chosen Young's modulus value and the strength values? And if so, what should you do in that case?
Can you repeat that again, please? The question. Are you asking about the effects of the Young modulus in our
You chose a value of Young's modulus and Poisson's ratio, stuck them in the model. When you went to do your worst case modeling, and you chose those models, I suspect from the mean values of the strength values of the weak rock. When you went to do your worst case modeling, you chose values for the strength, the variations values that were 2 standard deviations less than the mean. Do you think then that if you should have chosen a different value for Young's modulus in that case as well? If your Young's modulus was based off the mean, is there a potential relationship between, say, cohesive strength and Young's modulus?
Oh, yes, that's a very good question. Because here, for the provided values, we only got the Poisson ratio, and we don't have the Young's modulus. So we find it in the literature. So, if we want to take into account the standard deviation, like other parameters, then we also need to make assumption that what is the coefficient of variation. So yes, this is not we choose the Young's modulus based on the mean instead of the mean minus the 2 times standard deviation. So I would think that this will not impact much about the result, but we may expect that the strength will be lower because we want to consider the worst case modeling. So that means the worst case of the Young's modulus will be lower than this case.
Okay.
So I have a simple question, I think. You mentioned that at 62 meters, you expected some kind of failure, or possibly. Can you describe the expected failure mode? How would it fail?
Okay. So we said that at the terminal depth, let me find the slides here. So we check if the rock will fail around the terminal with this one. So around terminal, there's no radial stress, and we use more Coulomb criterion to see if this under this depth, if this rock will fail. So we'll realize that this overburden stress is too high for this weak zone. So because we can see that when theta is equal to 0 or 180 degrees, so it's horizontal. So it's the lateral wall of the terminal. So the stress here is over the more Coulomb criterion. So that means this rock will actually fail on the lateral wall. So this could still will be the key risk if we really need to excavate the terminal at this depth, because the rock is very weak and the depth here is about 60. So the overburden stress is high, much high, considering considering the rock here is weak.
Thank you.
Why did you choose Ka and not K opt?
Sorry?
Why did you choose for the lateral stress determination? Why did you choose Ka and not K naught?
Okay, so actually the K here is the given value here. So in the problem we're given, so the horizontal stress is 0.4 between 0.4 and 0.6 of the vertical stress.
Yeah, but why Ka and not K naught?
Oh, okay. Because here we only consider the overburden stress, so here the lateral stress will mainly be the active lateral pressure. So we use Ka to stand for the coefficient instead of the K naught.
Okay.
I guess just in the interest of time, thank you, Team GeoJackets, and thank you, judges, for your questions.